Okay, welcome back, everybody. Whatever time zone you're in, middle of the night, wee hours of the morning. We're at 10:30 here in US Central Time, Central Summertime. So I just wanted to add a little bit more, and then I'm going to go into what is a general equilibrium model. I wanted to say a few words about two approaches to demand side in general equilibrium models, which we associate with the names Marshall and Hicks. So I'm just going to do this by way of example. So on your screen, that's a Cobb-Douglas utility function between two goods, X1 and X2, and then there's a linear budget constraint where P1 and P2 are prices and M is income, and those are viewed as exogenous by the consumer. So the consumer wants to maximize utility subject to this linear budget constraint with a fixed income and fixed prices. If you do the algebra, Cobb-Douglas has this very simple property that the exponents alpha and 1 minus alpha are expenditure shares on the two goods. It turns out if you do the optimization problem. So alpha is the expenditure on good one, P1 X1 divided by M. So sometimes the Marshallian problem could be referred to as the primal in an optimization problem. I guess we don't use those words too much here. So that's a Lagrangian function then at the top line, maximize U equals utility function plus a Lagrangian multiplier times the budget constraint written in implicit form. So it equals 0 if you're fully spending your income. So there's three first order conditions. Everyone does this in, either final year micro and undergraduate or master's micro. There's three first order conditions corresponding to the three partial derivatives of this function. And I've written them out there. And the complementary variables are X1, X2, and lambda, which is often given an economic interpretation as the marginal utility of money. If you increase M by, what is the effect on in utility units, welfare units, if you increase M by 1 unit? And that's what lambda is in equilibrium. So, microeconomics exercise is always solve that problem for explicit demand functions. Xi is a function of P1, P2, and M. And those are referred to as Marshallian or uncompensated demand functions. Demand is a function of prices and income. This seems always the natural way to get a demand function because those are observed variables, P1, P2, and M. That's the way most people would look at it. But there's an alternative way that is, I admit, maybe less intuitive, but works very well in general equilibrium models because it allows you to automatically compute welfare and a price index, which is the Lagrangian multiplier, as part of the solution to the model. So this is sometimes referred to the dual of the Marshallian problem, which is to minimize expenditure necessary to hit a target level of utility. So U here is fixed as a parameter. You want to get a certain level of utility, and what is the cheapest way of doing that? So the Lagrangian multiplier then is multiplied by U minus the utility function. So this is a minimization problem. And again, there's three variables. And so the first order conditions are then given there. And you can work with those to first eliminate U and then solve explicitly for utility as a function of prices, solve for demand as a function of prices and utility rather than prices and money income. I remember being a student and wondering why anyone would ever want to do this. Okay, that's interesting. Can we move on now? And it turns, I think you'll see in a few minutes that this can turn out to be quite useful in a general equilibrium model because it allows you to compute. Whereas utility is being held constant here for the consumer, it's endogenous in the general equilibrium model. And so if you have, and the other nice thing about this is the Lagrangian multiplier has an interpretation as the consumer price index. So mu here is how much extra you would have to spend to get one more unit of utility. So it's the consumer price index. It's the cost of buying one more unit of welfare. Okay. And so if you use the Hicksian approach in the general equilibrium model, as part of the solution, you get welfare and the price index automatically. The Marshallian approach, you'd have to calculate those outside the model after you solve it. When you have many household types in different countries, this is really useful because you're getting all these things as part of the solution of the model. So I don't think we'll go through, I think we maybe should move on, but this GAMS file M2.-4, I believe you have that. No, that's not in there. Okay, well, I can provide that to you. Is it there? No. Oh, no, it's not exercise. Oh, no, I think that's a different M2. I shouldn't have used the same. Well, maybe it is. Anyway, maybe I should mail this to you. There's a lot of text here. I don't think it's worth our time to go through it, but it just contrasts the two approaches. The Marshallian approach, in which you can solve either, again, this is a simple problem where you're only maximizing one or minimizing one thing. So you can write this as an NLP problem, and that's what this file does. It shows you how to write. The first example is the Marshallian problem, where the NLP is maximizing W subject to the money budget constraint, M equals P1x1 plus P2x2 right here. Or you can solve it as a complementarity problem with the two first order conditions in the budget constraint. You can do it either way. And again, someone might say, well, why would you ever want to do it the second way? The first way seems so much easier. Well, the problem again is that in a general equilibrium model where you have different agents maximizing different things, firms, households, government, you can't write the general equilibrium model as an NLP because you're not just maximizing one thing. So then the second version of the model, it just shows how to do that as the Marshallian problem, where the objective function is expenditure, and as an NLP, you're minimizing expenditure subject to this welfare constraint that you want to hit the welfare level U bar with the minimum expenditure possible. Or you can write it as a 3-equation MCP, where the two first order conditions along with the welfare constraint constitute 3 equations and 3 unknowns. So you can do this either way. And as I've said, the most natural way is to think about this is, I think, the Marshallian way, because you observe income, but in a general equilibrium model, the Hicksian approach is just has advantages, as I've indicated, and I can see that in a little bit. Okay, so now I'm going to switch to the second set of slides. This last stuff, I don't think we'll worry about. This is in the files we sent. I'll give everyone a second to open that. This was called Madison Monday 2 PDF. It was not in the, not today. Yes, sorry. Yeah, that we sent a week ago. Yeah. So maybe I'll give everyone a few seconds here to see if they can open this one. Yeah, it was called Madison pre-course mailing. I hope it was there. Was it? Okay, okay. Yeah, no, it wasn't. The thing I sent this morning was just the exercise. Okay. Oh, it was in the zip file, Marcus and lecture slides that was sent a week ago. Okay. Okay, so this is an introduction to applied general equilibrium modeling, and illustrates a number of things. And this will take us, I guess, to lunch, and maybe we'll spill over till after that. Are we going to noon our time, Martha? But, yeah, okay. At that point, I will be hungry and starting to babble, so that will definitely be a stopping point. But I'm running a little ahead of time, so please, if you have questions, ask them, or the confusions just persist. So feel free to speak up and stop me if you have that question. Probably 5 other people do too. So happy to hear from you. Okay, so what is a general equilibrium model? Well, I don't know if there's any formal definition, but typically we have multiple interacting agents. Individual behavior is based on optimization. Most interactions are mediated by markets and prices. That is, there are externalities like pollution or other things that are not market mediated, or public goods provided by governments that people cannot choose quantities of, things like that. Equilibrium, well, I'm sure there's nice formal definitions by theorists of what an equilibrium is. So this is a sloppy, simple definition of equilibrium. It's basically agents subject to the constraints they face and what variables they take as exogenous cannot do better by altering their behavior. That is, they're optimizing, given the things they can choose and the things they can't choose. Markets, generally clear. So for example, supply and demand, supply equals demand in each market. So that's kind of my very simple definition of what is an equilibrium. And I'm sure there's much more formal ones in mathematical general equilibrium. So what are the steps in general equilibrium modeling? Well, I don't know. This is how I do it. I mean, first of all, specifying the dimensions of the model, and that may be given to you by your data. But how many goods are there and factors of production, number of consumers or different household types, number of countries, number of active markets, and so forth. A market, by the way, can be a trade link, between two countries in one good. You can think of that as good. A technology allows good produced in one country to be supplied to consumers in another country. Then choosing functional forms for production, transformation, and utility functions. And specification of additional equations, which we typically call constraints or side constraints, and we'll have examples of that later on. Then choices of inputs and outputs for each activity that may be, again, given to you by your data set. And then given this complementarity format, specification of initially slack activities. So for example, there may be many goods for which there's no trade between country I and country J, or certain technologies, say to produce electricity, are not used in the benchmark. But you might want them in there because policy changes or other changes might bring them active and make other things zero. Third step is construction of a micro-consistent data set. And I'll tell you in terms of an example exactly what that means. But in a simple case, it means the data satisfies zero profits for all activities, or a more general term is product exhaustion. Any revenues generated go to someone. So we can have monopoly with positive profits, but those have to be assigned to some agent in the model. And then secondly, data satisfies market clearing for all markets. So a micro-consistent data set is basically saying, this is a set of numbers that could be generated as an equilibrium by some model. And again, I'll get very specifically into that. Then the fourth step, and this is with big data sets and real data, this is 80% of the work. I don't know what you'd say, Tom. Yeah. Calibration is choosing parameters for those functional forms such that the model and the data are consistent. What do we mean by consistent? We mean that the data represents a solution to that model. Or in alternative language, if you run the model, it spits back those exact same numbers. That means you calibrated the model correctly. And that's called the replication check. Run the model and see if it reproduces the input data. And if it doesn't, something's wrong somewhere. Okay. And then once you pass the replication check, which is a necessary but not a sufficient condition for the model to be valid, then you can run experiments, changing taxes, changing tariffs, changing technology, policies, and so forth, and get quantitative estimates of the effect of those on different factor prices, different households, different countries. Okay, so I'm going to do this all by way of an example. And this is sort of what a trade economist would call a closed economy Hexagon model. There's two goods, there's two factors of production, which we'll call capital and labor. And those are in fixed supply. They're not variable. So households are not going to choose at this point how much labor to supply, how much leisure to take. And there's one representative consumer. So the term representative consumer means, well, there's 10 million of them, but they're all the same, meaning that we can treat them as facing fixed prices. So consumers are going to take their income and the prices for goods as exogenous parameters, but they're of course endogenous in the general equilibrium model. So the notation is there's two sectors, X and Y, they're final goods, two factors of production, L and K. There's no intermediate use in the example I'm going to give you. And one representative consumer who has a utility function, W, for welfare. Labor and capital are an inelastic or fixed supply, but they can freely move between sectors, which is crazy, but the way trade economists start. So there's four prices in the model: price of good X, good Y, labor, and capital. I is consumer's income, and PW will denote the price index of one unit of W. So it's the cost of buying one additional unit of utility, which in the Hicksian problem I showed you is the value of that Lagrangian multiplier mu. So these are the equations of the model. There's a production function for X, Y, fixed supplies, L star and K star of capital and labor, and then a utility or welfare function defined over X and Y, and a consumer budget constraint. So C and S is, sorry, inconsistent notation. I just said that was going to be I for income. It's the same here as CONS, sorry about that, which says that expenditure on goods is paid for by factor income from the consumer. So this is just a set of technical relations. This is not an economic model at this point. Any allocation of labor and capital between the two sectors can give us an X, Y, and W, but that's not an economic equilibrium in general. So what's missing in this model, this set of equations rather, is optimization by the individual agents in the model.
There is a question in the chat.
Okay. Yes.
I think the new parameter that goes in the math is analogous, or perhaps maps directly onto the Frisch parameter that some use to calibrate the Marshallian demand systems in modeling. Is that right?
That's a question for Tom, I think. Is that, I don't know the term, the Frisch parameter.
It's for income elasticity. I think this is unitary income elasticity. I will answer the question afterwards. I'll have a
Okay.
I copy that, this question was from Siwa. I copied the question and Tom will look into it, okay?
Yeah.
Okay, sorry, I can't answer the question, but Tom will do it. I'm not familiar with the term Frisch parameter, but we will get on that. Thank you. Thanks. And again, please feel free. We're doing well on time. Please feel free to ask a question. So this set of equations I wrote down with could actually be treated as an optimization problem. You could maximize welfare subject to all the other equations as constraints. There's actually sort of a theoretical justification for that called the first theorem of welfare economics, which says that a competitive equilibrium is Pareto optimal, and there's only one consumer. So Pareto optimal means maximizing that one person's utility. And actually some early approaches to computing equilibrium did this. One of the Japanese economists kind of used this and did an iterative procedure. Nigishi, yeah. But the usefulness of the approach breaks down quickly as the model becomes more complicated. We have multiple households, multiple firms, any form of tax distortions or imperfect competition it just doesn't work. So the alternative approach, as I indicated earlier, is to convert the problem to a system of equations or weak inequalities and solve that system. Those weak inequalities embody optimization at the level of the industry or the consumer. So the individual optimization is embedded in the model at the level of each of these inequalities. So
Can I ask a question?
yeah.
I'm just thinking about this from the first point of view, maximizing utility function, and coming from a DSGE background. If I was to do that, I would be thinking about, well, there's also a Walras law to worry about, so I would throw out one of those constraints.
Correct.
Do I do that as well in the dual problem?
So
Go ahead, Tom. Tom, you can.
and the key thing about throwing out the equations is recognizing that the model one determines relative, not the absolute price level. And so what it essentially means is that the system of equations is well defined. It's just that there may be more than one solution. You get better numerical performance if you fix a price index, which can either be a market price or an income level, and then solve in the remaining system. And this is what, in the complementarity model, which Jim will show you, if you fix a price, the system will automatically omit the corresponding equation. That equation will be satisfied at the solution, but the solver doesn't have to see it. It turns out that with more recent versions of PATH for small models, it doesn't really matter because it can handle the singularity, the fact that that the Jacobian is singular at the solution is not a problem for the solver. But, so that we typically, this thing about Walras law and fixing a price, we typically don't worry about that. We just write down the problem here, and then that's a numerical issue related to the solution of the problem. It's really not part of the theory of the model.
Right, and so the software handles that issue, whereas if I was trying to write this on my own without access to GAMS, then I would need to worry about that.
Yeah, my key sort of pet peeve with with Walras law, fix a price and you're off and running. That sounds fine until somebody writes a model down for you where you have privative tariffs and you have separate. Suppose you have multiple regions which choose not to trade because the trade costs are too high. Then you don't have one price index, you have multiple price indices for each separate economy. So there's no guarantee that fixing one price will solve this problem. So it's better not to worry about that initially, just relegate that to the solver to deal with the singularity of the solution. And so initially we don't need to really concern ourselves with that.
Yeah.
Okay, that makes sense. Thank you.
Okay. Yeah, I mean, my really short answer to your question is yes. There is a redundancy. If you have a set of prices that solve these models, any scalar multiple of all those prices is also a solution. So I typically would fix one price. Usually I take the consumer price index, which is a very convenient choice of numeraire. We'll call that the numeraire. And you'll see that in a couple of minutes. So I'll come back to that question in a little bit. But you're right. Yeah, absolutely. Okay, so kind of the way that I go about this basic general equilibrium model is to convert those technologies for producing X, Y, and the technology for producing welfare, the utility function, convert them into cost functions, which embodies the optimization at the level of that sector. So from the production function for X, you can solve for the cost function, which says the minimum cost of producing 1 unit of X is a function of the prices of labor and capital. Minimum cost of producing 1 unit of Y is a function of those same prices. And then on the consumer side, if we're going to use the Hicksian approach, which I'm going to emphasize today a lot, we solve for the cost function. We've traditionally given that a different name in economics. We call it the expenditure function, but it's identical to, it is a cost function. It's the minimum cost you have to expend to buy 1 unit of utility at prices PX and PY. So it's solved for in exactly the same way as production technology cost functions. So the next great crucial step is provided by Shepard's lemma, which allows us to get the demand equations for capital and labor and for X and Y by the consumer directly from those cost functions by simply taking the derivatives. It's called Shepard's lemma because it follows directly from the envelope theorem, I guess. So the derivative of the cost function for X with respect to the price of labor is the optimal or cost minimizing demand for labor per unit of output. And similarly for capital, and similarly for consumers' demand for X and Y. So this is a vital step in being able to construct market clearing conditions in the markets for capital, labor, and for X and Y. Okay. So then those set of equations, which were just technical relations, becomes an economic model with the optimization built in, as I said. So we have a general equilibrium, which is going to be a solution to a square system of 9 weak inequalities and 9 unknowns. These fall into 3 categories, and this is a very general structure that can be generalized to much, much more complicated situations. There are pricing inequalities or zero profit inequalities, market clearing inequalities, and income balance equations. And together those specify the general equilibrium model. In this model, in the Hicksian formulation, the unknowns are 3 quantities, X, Y, and W, 5 prices, and income. Formulating the equilibrium as a complementarity problem requires that each inequality is associated with a particular variable. The zero profit conditions, if they hold as a strict inequality, strict inequality, profits are negative, that activity is not used. So the complementary variable to a zero profit condition is a quantity or the activity level. If a market clearing condition holds a strict inequality, supply exceeds demand, then that's a free good. The complementary variable is price to the quantity equation. Complementary variable to an income balance equation is just income. That's really more a definitional equation in the model. So this is now the conversion of a set of technical relations into an economic model. There's 3 zero profit inequalities that unit cost is greater than or equal to price for 3 variables, X, Y, and W, and then 5 market clearing inequalities, which have the complementary variable of the prices, and then the income balance equation.
Aculos. Hey,
Sorry, someone ask a question? Was that an aside? Okay. Again, this is sometimes this Hicksian formulation is a little puzzling to people. We don't observe this welfare level, but I'll show you how we stick that in. But it's very convenient in the sense that this problem computes welfare directly as part of the solution and also computes the price index, which is this PW, P sub W variable as part of the solution. The supply, you can think it's just very useful, if not very intuitive, to think of welfare as a produced good. There's a technology that turns goods X and Y into welfare. It's in people's heads, but it's just a useful way of doing it. And then the supply and demand equation here is really the indirect utility function. It says that welfare is equal to money income divided by that price index, the cost of buying 1 unit of utility, which is in turn a function of prices for X and Y. So that's really the indirect utility function. The market clearing conditions you see here apply Shepard's lemma for capital and labor to get the demand for the optimal demand, cost minimizing demand for labor to produce 1 unit of X times the number of X units produced in equilibrium. And then also from the Y sector, the demand for labor is using Shepard's lemma, the minimum amount of labor to buy to produce 1 unit of Y times the total amount of Y produced. So this is now an economic model of 9 equations and 9 unknowns. And when we get back the question about the price index and the redundancy in Walras law, your question was correct. There's sort of an extra degree of freedom. That's maybe not, is that the right term? Yeah. So any set of prices and that solve this model, any multiple, if you double all the prices, it's still a solution of the model.
Prices on income. You have to scale income as well. It's a PL and PK double and I double.
Right. Yeah, I is really a definitional equation in the model. It's yes, if you double PL and PK, it automatically doubles I, but yes, you're right. Okay. So typically, as the question indicated, we fixed one of these prices, but there are some complications as commented. Okay, so next step. What is a micro-consistent data set? Well, it's micro-consistent when it satisfies the conditions for an economic equilibrium, meaning it could be generated as a solution to some model. So the data will have to, the numbers we're going to put into the model must satisfy 0 profits, market clearing, and income balance. In this model, there are 3 production activities for X, Y, and W. 5 markets for X, Y, L, K, and W, and then income balance. So I have a kind of technique that I probably got it from Tom way back, where we just create a little matrix, and the requirements for micro consistency in this matrix are very straightforward. So I just go to the matrix itself rather than read all this stuff. Okay, so I made the columns, the 3 production activities and consumer income, and the 5 rows are the 5 markets. Complementary variables to markets are prices. So I put the prices on the left-hand side. A positive entry signifies a receipt in a market or an output, and negative values signifies an expenditure or a cost or an input into that market. So I've just made up these numbers here. I've made up a very symmetric example, which makes it simple. So the X sector is going to produce 100 units of value. By the way, these are prices times quantities. This matrix balances in values. So the output of the X sector is 100 units in value with inputs of 25 labor and 75 capital. Y sector, oh, there's an error there. There shouldn't be a entry at this, erase this number. Unfortunately, that's a PDF. That shouldn't be there. These things sneak in. There's gremlins that sort of get into your files. That number should be 0. So the Y sector produces only Y. There's no intermediate use, but you can easily put intermediate use into this matrix. So the column for X could have a negative entry of PY. So that would be an intermediate input. Y uses capital labor. And then the W sector, again, it takes a little to wrap your mind around that. You just treat that as if it's a produced good. Inputs of X and Y produce 200 units of utility. The consumer column is the income balance equation. The consumer receives 100 units of value from selling labor, 100 units from selling capital to the production sectors, uses that income to buy the utility. So again, it took me a little while to get my head wrapped around this, but treating utility as a produced good and having a market is just really useful. Okay, it has a payoff in the model. Okay, so what is microconsistency in this case? Microconsistency is the condition that row and column sums are 0. So what is a column sum? Well, a column sum is this zero profit or profit exhaustion idea that anything received in value has to go somewhere. So in this case, there's no profit income that goes to an agent. All of revenue is paid out to capital and labor. So a 0 column sum product exhaustion. For W, again, thinking like it's a produced good, the W sector buys goods, X and Y, and produces an output of utility or welfare. And then the consumer column is income balance, that the income received from selling labor and capital is used to buy utility. Okay, so then the row sums, what are row sums? Row sums are market clearing. So in the case, ignoring that typo in my slide, X produces 100 units of input, of output, and it's purchased by the utility sector. The row sum is 0, meaning that the demand for utility equals the supply. Or sorry, the demand for X equals the supply. Similarly for the Y column, and similarly for welfare. And labor and the supply of labor and capital from the consumer equals the demand for each factor of production from the 2 sectors. Okay, so the row sums are market clearing conditions. The column sums are 0 profit conditions and income balance. So this matrix satisfies that. And what to do when your data doesn't satisfy that is a more advanced question. I don't think we have a least squares. I actually have an example of that in my model library.
It's not a coincidence that the number of column sums and the number of row sums equals the number of equations in the model, right? There were 9 variables and 9 equations. It was a square model, and
right.
And those equations are now reflected in those columns and row sums.
Yeah, I hadn't thought about that. That's correct. In more complicated models, we could have added equations, say in a model of imperfect competition, we could have an added column for a markup formula.
Right.
So there are times that there's added equations, added unknowns that wouldn't show up here, I guess.
And I can also see in this case where if I were to double all the prices in the model, I would just increase every single value in that table, multiply it times 2,
Yep.
and everything would still sum up to zero.
That's correct. That's this Walras law or
Yeah,
redundant equation model. What I'm going to do, don't like forward references, but to get rid of that indeterminacy, typical way is to fix one price, and then that equation that's complementary to that variable is dropped with the model, and I'm going to fix PW. And that is advantageous here because then changes in the price of labor and capital are interpreted directly as real prices. So if PL goes up, that means your real wage has gone up. It's gone up in terms of the cost of buying utility. But yeah, you double all prices and every number in that model just doubles. That's right. Okay, so then kind of the last step is calibration, and that's making these numbers consistent with the functional forms. I've chosen really simple functional forms. Tom kind of hates it when I do Cobb-Douglas, but it's only a teaching technique. It's a pedagogic simplification here, because with Cobb-Douglas, those exponents in the Cobb-Douglas function are expenditure shares, and they come directly from that matrix. So it's just real easy for teaching purposes to see where those numbers come from. So for this is the dual, this is the expenditure function. Cobb-Douglas also has the real nice property that, well, sorry, all CES do. If the primal problem is CES, the dual is also CES. We call that self-dual, I guess. So if the expenditure function and the cost functions are Cobb-Douglas, sorry, if the production functions and utility functions are Cobb-Douglas, expenditure function and cost functions are also Cobb-Douglas. And the share parameters we need to calibrate the model are found directly in that data matrix because those are shares. So this little data I made up, the expenditure shares on X and Y are 50-50. So the expenditure calibration of expenditure function is PX to the 0.5, PY to the 0.5. These shares for X and Y give the exponents for the cost function for the unit cost functions for X and Y. X is capital intensive in standard terminology. Y is labor intensive, and those will show up here and will show up when we run the model. So Cobb-Douglas is pretty restrictive, but it's very simple for teaching purposes to just see exactly how you move then from the numbers into the functional forms that will reproduce the data. Then for the market clearing conditions, we need to, for example, know the amount of labor demanded in the Y sector. And that's found by just applying Shepard's lemma to the cost function. Multiplied by the equilibrium output of the Y sector. It can be simplified a little bit like this. Can be simplified a little bit more directly. That looks like another mistake. That should say PY, not PX. Oh boy. But these then, you can see the utility again of the Shepard's lemma and allowing the creation of the market clearing conditions once you have the correctly calibrated cost functions. This turns out to be a very general framework. So just let me spend 1 minute on that. A lot of this is due to Tom Rutherford and Lars Matthiessen, I guess, who really came up with this way of doing general equilibrium. When I was a boy taking graduate microeconomics, general equilibrium theory was almost completely non-operational. They talked about existence, uniqueness, and stability, and there's nothing you could do with it. No one ever solved the general equilibrium model until maybe Herb Scarf came along or something. But this framework with these zero profit conditions, market clearing conditions, and income balance relations turns out to be generalizable to much, much more complicated situations. And on my website, it's available for you to use our big model libraries and notes, incorporating taxes, subsidies, quotas, licensing, doing things like equal yield tax reform, generalizable to multiple household types, setting endogenous taxes for income redistribution targets, public consumption and intermediate goods, pollution, production externalities, or infrastructure provision, increasing returns in imperfect competition. I've done a lot of that in my career, and especially with endogenous multinational firms and foreign production. And you can do this either in a monopolistic competition framework or in an oligopoly framework with or without free entry. And then, of course, open economy models in which you just have added production facility, added production activities that consists of an input of one good in one country and an output of that good in the other country. And putting transport or tariffs on those added production activities. Okay. So well, I should pause there. Let's take a long breath if there's any other questions, and then we'll actually go through this model and two extensions of it, which we may or may not get through this morning, but or this night, wherever you are in the world. So I'm going to take a breather here for a bit. Any questions you'd like to ask so far? No? Tom wants to say, oh, Tom, go ahead.
Well, I think it's great. I think it's that today's workshop, today's focus of today's workshop is basically trying to help people get started with things. And I think I really like Jim's stuff. During Jim's lecture this morning, talking about the impacts, I was thinking we should come up with, the optimal design problem that you just mentioned. It's an interesting problem in this thing, designing optimal tariffs. Mentioned as one example. So during the little workshop here, I put together an exercise for people who may be interested in sort of investigating, learning more about that. So I've come up with a little example, and I'll send that away. And this is less for people if you've worked with GAMs before. This sort of an exercise that would be different. But our main objective is to basically introduce the basic thing.
Okay, yeah, well, maybe we can do that. I'm kind of running ahead of that, but I
could go through them. It would be helpful.
well, let's not do it now. Let me go through these.
Yeah, go through these guys.
And
this is just something for people who are sitting in the
Yeah.
workshop who have used them before distribution. This is something to sort of make a little example.
Yeah. No, the MPEC thing is great for, it used to be that we would try to find an optimal tax by brute force, by, searching over and then refining a search. And, like Randy Weigel and I have a paper in the JPE 1989, in which we have to iterate over solving the model and, looking for welfare and then refining it and trying to find, a Nash equilibrium for two countries, and where they both imposing sort of Nash optimal tariffs.
That's a great point.
A tiny number. It was well before its day, I'm afraid. well down in citations. All right, so I'm gonna, so these were, you should have these files. So I am going to stop sharing screen. Ooh, that's a nice picture. And where? Do, let's fix my. So I'm going to open the zip file of GMS files that was in the mailing a week ago. This is file Madison 1, which is the model we just went through and explained and looked at the data. Oh, yes, yes. Did I inadvertently close? Do I do this again? No. What did I do? I think I may have inadvertently.
You're still in
Oh.
the Zoom meeting. So
Okay, go ahead.
share, you just need to decide which one. Do you want studio? Which
yeah.
one do you want? Okay.
Oh, okay, beautiful. So there's a little comment. So in GAMS, there's two ways of making comments that are ignored by the model, sorry, by the compiler. You can put a star in the first column, has to be in the first column, otherwise it's a multiplication sign. Or, you know, that gets inconvenient if you have a whole block of text. So you can use the command I have here. You can say $ on text, and at the end you can say off text. So then you can edit it, you can rearrange it without having to, you know, keep moving stuff and having stars in the first column. It's just convenient if you have a block of text, and that simply is ignored then by GAMS. It will be printed in the listing file, but it's ignored. So this model, we're going to actually put those numbers in the functional forms. You don't have to. You can declare parameters and give those parameters values. But again, for teaching purposes, I'm trying to keep this as straightforward as possible. So for now, we only have two parameters, which are the labor endowment and the capital endowment. I call them L bar and K bar, and I assign them values of 100 each, which is the calibration from the little matrix, which I've reproduced. It's not reading these numbers at this point, just a text file, but you can actually read these numbers in, and I have examples in my model library where you do that. Read it in, say, from the Excel file. So there's 9 non-negative variables, 3 production activities, 5 prices, and then the income. The equations of the model, I've written them sort of so that they correspond in order of the non-negative variables, but you don't have to do that. There's no need to order them in that way, although in the listing file, it will follow the order of the variables. So. And so then again, the equations are written, you give the name of the equation, ... tells GAMS that an equation is coming. And these are all written in the greater than or equal to format, except for the income equation, which is really just definitional. The 3 zero profit conditions are unit cost of production greater than or equal to price for PX, PY, and PW. And then L bar and K bar are the supplies of capital and labor on the left-hand side. The right-hand side applies Shepard's lemma to the cost function, unit cost functions above them, multiplied by the output levels X and Y. So demand for labor comes from both the X sector and the Y sector. And similarly for capital. And then for commodities, X and Y are the supply, they go on the left-hand side. And on the right-hand side, apply Shepard's lemma to the expenditure function to get the demand for labor and capital, for X and Y times the welfare level in equilibrium. And then the supply of welfare equals income divided by the price index, the cost, the minimum cost of buying 1 unit of utility. And then income is just derived from selling capital and labor to the market. You can extend this to endogenous labor supply quite easily. I have that labor leisure choice model in my model library, so it's there. So then the model declaration, I call it close. You can call it anything you want. Doesn't have to have the name of the file, as long as it's the same name that's in the solve statement. And it's slash name of equation dot complementary variable, comma. I think in the new version, you don't need the commas, but you can use them. And finally, we get to the question about price and Walras law and numeraire. Again, any set of prices that solve an income that solves this model, any multiple will also solve that. So, you could, the problem with not correcting that is that the model just solves for an arbitrary set of prices. Relative prices are the correct relative prices, but the price level is sort of arbitrary. And if you do a counterfactual, say changing the supply of labor, it could jump to a different price level, which would be very confusing. So it's just good practice to pick one price as numeraire. And for this model, the most convenient thing from an economic point of view is to fix PW, because that's like consumer price index. That's how much you have to spend to buy 1 unit of utility. So it's a really convenient choice of numeraire. And then when the price of labor changes, well, that's a real exchange rate. That's how much your wage has gone up in terms of the basket of goods that you want to buy. So it's just a very convenient choice. The problem is when you have multiple countries and multiple households, you can only pick one. I have this big simulation model of many goods in many countries that has 36,000 equations and unknowns. It's all done in sets. Believe me, you don't have to write them out. But there's, out of 36,000, there's one extra equation. And you choose one numeraire. If you choose one country's price level to be fixed, or then you have to compute them for the other countries after you solve the model, basically, okay, which isn't a big deal, but you can charge everything. Okay, nonlinear problems. It's important to set starting values that are at least non-zero. You may not, in some cases, you may not know what they are, but just set them. And the notation is this .L notation, which is not, again, I've said it before, it's not fixing the variable, that's .fx. This is just setting a level, which then will be changed as the solution algorithm goes through. Did you want to? Okay. I was going to postpone this. Maybe you should just ignore that. There's a technique for finding calibration errors. Yeah, no, just ignore this for now. So solve the model, ignore this interlim statement for now. Maybe we'll go into it sometime later. Solve the model, see that it replicates the data that you put in, or the numbers we think. These starting values are in fact the solution values, or that's what I think the solution values are. So solve the model and see that that's what you get back. Then here's an example of a counterfactual, double the endowment of labor in the economy and see what happens to these prices. Double the endowments of capital and said, this is a very symmetric model, so you should see symmetric outcome. And then double both endowments of capital and labor. And this is, theory tells me what this should look like because everything has constant returns. Everything's homogeneous degree 1. If we double both factor endowments, your theory should tell you that you double all real variables and all price variables should be unchanged. Okay.
That's just because of homogeneity. Everything goes up
Yeah.
proportionally.
So sometimes I do these things. I do stuff with my model when I'm working on a lot more complicated case. I give the model a question where I know what the answer should be. And if I get something different, I know either my intuition is wrong or my coding is wrong. Back to basics. I'll postpone the next part for a minute, and let's just run this this first case. And if I want to stop the model, I can say $ exit, so that if there's a lot more to come, I can just get this first part. Okay, so I ran the model. The first two are just replicating. So this is passing the replication check. This is the numbers I put into the model, and it's spitting back those things as the solution to the model. Okay, and all those marginals should be 0. So then the first counterfactual was to double the supply of labor. And this is the result. Welfare less than doubles, because you have a fixed factor. This is like general equilibrium diminishing marginal product. X goes up by less than Y. And I would ask my students, why, not why? WHY, is that the case? Because why does Y go up more than X? Well, that holds prices. It's not quite Ripchinsky at this point, but yes, no, it's because Y is the labor intensive sector. So that added Y is more useful in producing Y. Too many Y's here than it is in producing X. W is numeraire, so these price changes for labor and capital are real values. So labor suffers, this is the immigrant problem, right? So all these extra laborers appear and the wages of the locals go down. Okay, that's a consequence of the structure of the model. And the return to capital, capitalists love this. Capital goes up by 41%. It's real income. So that's something that should seem pretty intuitive. Second counterfactual sets labor endowment back to its initial value of 100 and instead doubles the endowment of capital. And this, you see, it's a very symmetric model. So numbers for X and Y and labor and capital just reverse, which should also be intuitive. Now, I should better explain the marginal in this case. The solver has a convergence limit. Is that what you would call it? A default. And it'll stop when it gets really close to the solution. But for the individual equations, it might leave a little bit of residual. And those things in marginal to the -8 are just an artifact of the convergence tolerance.
Tolerance usually, default tolerance is 10 to the -6. So those are all very, well, we have a very precise answer. -8 is a really small.
Yeah, so we just ignore that. This is a valid solution, even though something's appearing in the marginal column. It's just the convergence tolerance that exits the solver, tells it, okay, we're close enough. We'll quit. And then testing this homogeneity idea, the last iteration was no, what's that? Yeah, so this is the last iteration, was doubling both factor supplies, and because of all the homogeneity in the model, that should double all real values and leave all price variables unchanged. And that's what we're getting. So I'm pretty confident that I did the model correctly. You know, this isn't a good thing to do. And when you're making up simple examples for yourself, there's checks that you can put in to make pretty sure that you've done your economics correctly, and you've done your calibration correctly. That's a set of numbers we want to see. Okay, so then this model has a second part. I'll just erase the exit sign, or I could star out the exit sign. And this is to convert the model to a small open economy model. And I'm not sure I should have done it this way. I don't put in the trade activities. But this is what we would call a quick and dirty conversion. I'm simply going to change prices of X and Y from being variables to being essentially exogenous parameters. And the way you do that is with this FX notation. So this says set the prices, fix the price of X and fix the price of Y at 1, which are their initial solution values to the model. If you do that, you better you have to unfix the price of welfare. Not really, because it just drops. I don't think I need to do that. What's the numerator going to be? Oh, it's going to be in terms of prices.
You're fixing both X and Y prices. Therefore, the W price I think is fixed as well.
Yeah. Yeah, okay. Right, because PW is only a function of PX and PY. Okay. So solve this model, and then we can do two things that you're taught in undergraduate international trade theory, which are, I'm starring off the on-text, off-text, which is effectively
You
removing
need
them.
to start before the dollar
Yeah.
sign.
All right. Which is to, let's see if the Rybczynski theorem you're taught in undergraduate international trade works. And let's see if the Stoper-Samuelson theory that you're taught in undergraduate trade theory works. What does the Rybczynski theorem say? It's actually a sort of partial equilibrium result. It says holding commodity prices constant. This is where I could use the blackboard, but if you increase the supply of one factor only, you get a more than proportional increase in the output of that factor, that good, and an absolute decrease in the output of the other good. You get this very biased change in outputs from a biased change in the endowment of only one factor. I get Ron Jones in a classic article in the early 60s called this a magnification effect. That the change in the factor endowment is actually magnified in the outputs. That one good actually goes down in its output level. What does the Stoper-Samuelson theorem say? Well, set L bar back to its initial value. Stoper-Samuelson theorem is the dual. They are mathematically equivalent theorems in this model. The dual says holding those factor endowments constant, if you increase the world price of one good, you more than increase the return to the factor used intensively in that sector and absolutely decrease the return to the factor in the other sector. So again, it's a magnification effect. You increase one price and the effect on factor prices lies on the outside of that in zero. So let's see if this works. Okay, so I'm going to run the model. And I don't know how you easily get, is this the right one? And so, yes, so here, when you use the FX notation in GAMS, you're actually fixing the upper and lower values of those variables. So you see lower value fixed at 1 and upper value fixed at 1. Okay. And PW is now an unfixed variable. So running that model with the fixed prices being the initial solution values, nothing happens. You open up the world to trade. World prices are the same as your domestic prices. You could trade, but there's no beneficial trade. You know, the rest of the world is just a carbon copy of your own country. So the first counterfactual is the Rybczynski theorem, double the price of, double the endowment of labor in the model. And what happens, remember the solution values initially were 100 for each of them. The output of Y more than doubles and the output of X actually goes down. And that's this magnification effect. That's the Rybczynski theorem. That it lies on the outside of one sector doubling and one sector being zero. You get this bigger gap in that. The fact that world prices are fixed means that factor prices don't change. And this is kind of an important thing in a lot of policy analysis, that you can an open economy, a small open economy can absorb added factor supplies without diminishing returns, because you change the composition of output, absorbs all that that extra endowment of one of the factors. I've tried to explain this to labor economists with very little effect. Well, actually, you can absorb those. You just change the composition of output and produce a lot more of that labor-intensive good. Okay, so
What's the
then,
marginal on the PX and PY? Does that show somehow trade flows? Yeah, so there you go. You have exports of 100 units of PY. No, 100 units of PX and imports of 100 units of PY.
right, no, good point. Yeah, so the marginal is the imbalance. So the nice thing about the coding when this was written is that it's, even though you're technically dropping those equations, it still reports the imbalance in that equation. Yeah. So the complementary equation to PX is supply minus demand. So that's negative. So that's an import. That imbalance is the imports. And for PY, that's the labor intensive good. You're exporting that. Supply exceeds demand by 100 units. So yeah, so that is giving you your international trade. This isn't a great way to do it because, you know, you're going to put tariffs and transport costs on these variables. And this was just a kind of quick trick. And so welfare doubles now, goes up by 50%. There's no diminishing returns. Diminishing returns goes away by changing the composition of your output. It's kind of cool, kind of a cool result. So we sent the labor endowment back to the original value and increase the price of X by 50%. So that's the world. We think of that as the fixed world price. So the economy shifts toward producing more X and less Y. The price index goes up, but that doesn't mean you're worse off. You're better off by that because you can now export, you create trade where there was none, and that's beneficial. Welfare goes up by from 200 to 216, so it's 16, 17% increase in welfare. Now here, these three lines illustrate the Stoper-Samuelson theorem. The price index has gone up, but that's not a bad thing in this case. It goes up to 1.22 from 1. But notice that if you these changes in the prices of labor and capital are outside of the change in the price index. Okay? That's the magnification effect now working on factor prices. So the price of capital, that's the factor used intensively in the X sector, goes up by more than the price index. So the real price of capital goes up. It's PK divided by PW. But the real price of labor goes down to 0.18 divided by the price index. So it goes down quite a bit. And this is the Stoper-Samuelson theorem that says, well, there's aggregate gains from trade. The price index for welfare for the country rises, but it's very unevenly distributed. If labor and capital are actually separate household groups, one group is worse off, absolutely worse off. And when international trade economists do policy, they like to ignore this sometimes.
That's the reason that WiNDC exists, is to explore these distribution consequences of
Yeah,
household differentiation of endowments.
Yeah. and people have done really interesting work now using things like scanner data where, different households, and they can identify household types and both their difference in preferences and how they're affected by different prices. And so this is sort of a pessimistic thing about trade theory that says, there's losers, even if there's aggregate gains.
Most of the G models suggest that who's winners and who losers is less about their expenditure and more about their income. That's the purpose of the model. Tomorrow we'll do some exercise to show how to decompose that. How much of it's due to prices and how much of it's due to factor prices and what's happening with the price heterogeneity. Because you have in the data set, you have heterogeneity on both sides.
Yeah, right. So people conjectured with the imports of cheap manufactured goods from China, people, there was this conjecture that low-income households face a tension because maybe their income will go down. Low-skilled manufacturing jobs disappear. On the other hand, they can go to Walmart and buy this stuff for a lot less money than they used to have to pay. And how is that tension resolved? And it's nice work being done on that. Okay, we'll talk about that tomorrow. Okay, I'm done for the morning. There was, I guess, yeah, one minute to just look at a table of those numbers. Oh, I want to go back to the slides. Where are the slides? Oh, they're here. So if you look at the slides, this just put those models in a table form. And I probably dumped those to Excel. The code, I think, is not there. But so this looks at the benchmark, doubling labor, doubling capital, doubling both endowments. And then this was the small open economy parable where I just fixed the prices, benchmark, double labor endowment, increase the price of good X by 50%. Increase the price. Oh, I should have gone to that one. This, this third line in this actually shows the computation of the corner solution. So this is, the third line is where the price of X goes up so much that you stop producing good Y, the labor intensive good. Price of X, economy completely specializes in X. At that point, further increases do nothing to factor prices because all your factors are in one sector. And welfare rises linearly or something with, or, you know, nice and monotonically with that price. So I should have shown that in the GAMS file, and you'll see the marginal on the Y equation. Y is unprofitable at those prices. I won't go back to that.
Stay on lunch break.
Okay. And reconvene 1 o'clock Central Daylight Time.
So I sent around this, I sent you a copy of this
I
file.
will send it to
So
you.
that's-
Okay,
Okay,
we'll be back at 1 o'clock. We'll have a lunch break now.
yeah, great.
Okay, thanks everyone.
Excellent, Jim. Very good.